So in this lecture, we will take a quick look of conservation laws that we learned in various chapters like fluid dynamics, electrodynamics, electromagnetic wave, and we try to understand what are conservation laws in quantum mechanics. So before we start, let us look at conservation laws in fluid mechanics. So let us talk about conservation of mass. Okay, so what is conservation of mass? So conservation of mass says that if there is a particular mass in a particular surface inside a particular container, and if there is a leak, if there is a flow of mass outward, then the rate of decrease of mass can be written in the way can be connected with the flow. Let me give you an example. So consider this is a cylindrical surface, okay, and consider this has fluid inside it, and this fluid is flowing out with a velocity v. So if the fluid is flowing out with a velocity v through this area A is the area of cross section, then it means I know that mass inside is decreasing. Okay, mass inside is decreasing. So how can I write this? Okay, in 1 second, let us see in 1 second how much of liquid is flowing. In 1 second, the amount of liquid which is ready to flow out is this. So this is the length v into t. So if I consider not 1 second but t seconds, okay, then vt gives this length, and if you multiply with area of cross section, then you get the volume of this. Okay, so you have a rho, that is the density of water, say, then you have to multiply with volume. But what is the volume? Volume is v into t into a. So this much of water in this volume is ready to flow out. Okay, so this is the mass flow. This is the mass flow. I mean, in t seconds, this much mass or of water is flowing out of this cylindrical tube. Okay, let's write it in a neat way. Okay, let's write it in a way we can extract more information out of it. So let us write it in differential form. So imagine I take the t on the denominator of the left hand side, then I can say that a rate of change of mass with respect to time is equal to, now there is a minus sign because the mass is decreasing inside the tube because water is flowing out. So minus of integration rho v dA. Okay, so the a becomes integration dA. This is just a style of writing. I am not being precise here with the directions of flow and the vector representing the area. All those things you will learn in fluid mechanics, so I'm trying to be as simple as possible. So you see, actually this object can be written in a more complicated way. This object should be written as like this: rho v n cap. N cap is the direction of the velocity, and dot dA. This is a more precise way of writing, and that is the reason why it is here, because see, if your area is like this and the liquid is flowing at a particular angle, then the flow of liquid will be given by this. This is accurate when liquid is flowing perpendicular to the area. So or you can say it is flowing parallel to the area vector. So this particular cross section is represented by area vector in this way. If the liquid is flowing exactly parallel to the direction of area vector, then n dot a dA will be removed. I can directly write this expression. Okay, anyways, just forget it if you don't like what I said. Just remove all these things. Okay, and concentrate here with the simplified version. Okay, Now this is the law of conservation of mass. It says that if there is a decrease in mass in the tube, it means there is some flow which is happening. This can be written in a more better way. So d by dt. Now what is mass? Mass is integration rho dv. Okay, rho is the density. If I integrate it over dv, it means I'm integrating over the entire volume of this cylinder. This will give me the total mass anyhow. It's a new way of writing, minus integration. Now here I'm going to use Gauss divergence theorem. Okay, if you remember Gauss divergence theorem, then this surface integral, this is a surface integral because this is dA. This surface integral can be converted into a volume integral by introducing a divergence. So del dot rho v, and this is volume integral dv. So what is the final expression? The final expression says d rho by dt, that is rate of change of density, or you can say it's just like mass conservation written in a new way. So d rho by dt is equals to minus del dot rho v. So rho v here is our current. You can say this is the current of fluid flow. So if there is a current of flow, then something must be decreasing because of this current. What is decreasing? Indirectly, this is the mass which is decreasing. So this is all about fluid dynamics. Let's talk about conservation of charge. So we have discussed this in great detail in our electrodynamics chapter, but here I'm just describing in short. Conservation of charge. So charge conservation. So consider you have a sphere, and inside the sphere you have charge. Agreed? Say the charge density is given by rho. Now suddenly what happens is these charges, they start flowing out of this sphere perpendicular to the sphere, and they are going out. So if the charge inside the sphere is going out, then I can say that the charge is changing inside the sphere. And how it is changing? It is actually decreasing. So I put a minus sign. And why is it decreasing? Because there is some flow of current. So this is conservation law, charge conservation law in electrodynamics. So because of this current density, what is this current density doing? The current density means there is a outward flow. Current means flow of charge. So current density is nothing but current per unit area by definition. We have talked about this in electrodynamics. All I want to say is here, if I have a current, it means there is a flow. And if there is a flow, then at one particular region something must be decreasing. In this case, current means charge flow. So inside the sphere there is a decrease in charge with respect to time, or you can say there is a decrease in charge density. This is your charge conservation. Then there is one more interesting conservation law, that is the this is second. Third, there is a conservation of energy. Okay, so there is a law that talks about conservation of energy, and we have talked this in great detail in our electrodynamics lecture series. So I'll just give a quick review. Let's talk about EM waves. What do EM waves carry? EM waves carry energy. Any wave carry energy. Specifically, we are talking about EM waves. In EM waves, there is an interesting thing called the conservation of energy, which says that if there is any decrease in energy in a particular region, then this is equal to some flow of energy which is outward. Now what is the expression, or what is the quantity which talks about flow? That is Poynting vector. Okay, Poynting vector is that quantity which behaves like the current J we talked previously. Okay, so this is conservation law that says that any decrease in energy in a particular region is happening due to a flow of energy, and the flow of energy is described by Poynting vector, and this is the conservation law in EM wave. So now I think you are very much clear what conservation laws are trying to say. Okay, now let's talk about conservation law in quantum mechanics, and this is probability conservation. Probability conservation. So what probability conservation is saying? Okay, so what is quantum mechanics? Quantum mechanics has something called as psi that represents a particle, and psi square tells you what is the probability to find a particular particle in a particular region. If you do psi square dV, then it means you are asking what is the probability of finding the particle in a small region dV. So in a small region dV, the probability of finding the particle is given by this expression. Now something interesting happens in quantum mechanics. What if I tell you that there is an outward flow of probability? I know it's weird, but just bear with me. So there is an outward flow of probability, and because of this outward flow of probability, it means something is happening to the particle, or somebody is disturbing the particle or the particles in such a way that the probability of finding the particle in this particular dV region goes on decreasing with time. Something is happening, some kind of current or whatever, because of which the probability is decreasing. Okay, then I write the probability conservation law is like this. So del rho divided by del t, where rho is the probability density, you can call it. Better you call it probability, which is where rho is actually given by a mod of psi square, which is nothing but psi star psi. Okay, so this decrease in probability is happening due to some flow of probability outside the region. It means there is the probability is flowing from inside the region to outside the region. Now question is, look, what is J? Which quantity behaves as current here? See, here also we had a weird thing. The Poynting vector behaves like a current here. It is quite weird. We discussed in great detail in electrodynamics lecture series. So now question is, what is J in quantum mechanics? So the mathematical quantity that behaves like the current density is given in this way. So J is I h cross divided by 2m psi gradient psi star minus psi star gradient of psi. I know it's a bit non-intuitive. This comes from purely mathematical considerations, okay, but it will become more intuitive when we look at some scattering problems. But for now you need to understand that in quantum mechanics, if the probability of finding a particle is decreasing with time, then this means that there is some current which is flowing, and this current is decreasing the probability, and this current is decreasing the probability. It means this current is related to probability. Okay, see, in fluid the current was related to mass, you can say like that. In electrodynamics the current was related to charge. In EM wave, that is conservation of energy, the current was Poynting vector and it is related to energy. Similarly here the current is J and it is related to probability. Okay, so in the next lecture we'll try to derive this object, why J is in such way, we'll derive it. Okay, so I hope you understood the main idea behind conservation laws in quantum mechanics, and our next target will be now to derive this conservation law.